Okay, yeah, so last time we talked about partitions. So if you take an interval, then a partition, first of all, it has to include the two endpoints. And then other than that, all the other points inside it tell you how you cut up the interval, right? And for the most part, we kind of pretend that partitions are sets and that we can do all the normal set theoretic operations on them. We can intersect them, we can union them, these sorts of things, subset them, right? We can relate them. But with the additional caveat that we're always going to assume that the partitions are ordered, right? So if I say that a partition has x1, x2, x3, x4 in it, then I'm assuming x1 is less than x2, x2 is less than x3, and so on and so forth. That way I can write, x3 minus x2, and I know that that number is positive because x3 is bigger than x2. Okay, so that's kind of like the first thing that we remember there. Then we talked about, upper and lower Darboux sums. And so you take a partition, you find the infimum and the supremum of the function on each partition, use that to compute a rectangle, and that gives you an approximation of the area under the curve. Where does what come from? Oh, okay. Yeah, oh, sorry, probably the notes here. This is the last part of yesterday. So what I wanted to do is just show you, because everything where it says in this case there's a unique number called the integral, blah, 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 we have to prove that part, right? And so I said last time I would prove it, but we just didn't have enough time. Okay, so we proved some stuff about upper and lower sums. Yeah, no, this isn't, this is just the last part of last lecture. So that's what we're going to do first thing here. We are going to prove that the integral exists, and we're going to prove that it's unique. I might skip the uniqueness proof and leave it for you, but it's basically a simple consequences of the sup and inf being equal. And yeah, that's about it. And of course, you can actually define integrability as the sup of the lower sums being equal to the inf of the upper sums if you want to do that. That's what it means for a function to be integrable. And then, the integral is that value. If there's a removable discontinuity, it's not integrable. So you're saying if you have a function with a removable discontinuity, you could totally still be integrable, right? So for example, here, let me go to today's thing. I'm gonna, I'll erase this in a second. But so for example, this function is, that's definitely integrable. This function, that's definitely integrable. So there are lots of continuity. Turns out continuity is related to integrability, but not in an obvious way. So we will talk about this. Basically, there's a theorem that says, first of all, if you're continuous, then you're for sure integrable. Of course, these aren't continuous, but if your discontinuities are small enough, like there's few enough discontinuities, then you're still integrable. So for sure, if you have finitely many discontinuities, then you're still integrable. But in fact, it goes a little bit further. If you have measure zero discontinuities, then you're integrable. And we have to figure out what measure zero means. But yeah, if your function is only finite, has only finitely many discontinuities, you're definitely still integrable. And we'll actually prove that, right? So that's something that we'll actually do. So that's a cool thing. It says in some sense that every integrable function is almost continuous to some extent, right? So, and in fact, if you go and you do something like, 136, they only talk about continuous functions when they talk about integrability. And that's just because, talking about measure is too difficult. And you go and you look at most textbooks, they'll state the fundamental theorem of calculus in terms of continuous functions, and that's bogus as well. So for many, if you go out into the world, most people, you're going to see the proper fundamental theorem of calculus and the proper notion of integrability. The majority of people do not see that just because they're not taking, a rigorous enough course in order to be able to talk about those things. And even then, we're not going to be as rigorous as we could be. Okay. But this continuing to affect the value of the integral, since it's just, so if it's removable, no, right? I mean, if it's a jump discontinuity, you can see that's going to make a big difference to the, area under the graph. But no, yeah, you're right. If it's a removable discontinuity, basically the idea is that, well, whatever that discontinuity is doing, it doesn't really seem to be contributing to the area under the graph, right? Like that discontinuity is a single point. There's no real area under it. So it doesn't affect it? Absolutely, you're right. And it's going to turn out that if I give you two functions, and let's say those functions are identical, like they're the same function, except at a finite number of points, right? So I give you a function f, I give you a function g, and I say f and g are almost the same function, but there's just a finite number of points where f and g are different. Then the integrability of one function will imply the integrability of the other, and their integrals will be equal. And that's something we can prove too. And the proof is actually not too bad. But again, we kind of need to talk about a measure before we do that. Actually, you could do that without measure, but it'll be, I think, probably a little bit easier when we do talk about measure. Yeah, so good. Yeah, these are great questions. It's awesome that you're all thinking about this. I like it. See if you can prove it too. Like that would be the next step, right? See if you can do that. Yeah, because those are not like outside of your, they don't require tools that you don't have. The proofs are a little bit sophisticated in the sense that you're just not used to it, but in a couple of weeks, those will be proofs that you're like, oh yeah, okay, I get how we would do this. Okay, so today we want to prove that if your function is integrable, namely you can make the upper and lower sums as close together as you want, then that means that there's some number between them, right? So what do we want to prove? So we want to prove that if, for every epsilon greater than 0, there exists a partition. So I'm just, kind of using the same setup that we had at the end of Tuesday. Right? Okay, so this is the definition of integrability, right? So for every epsilon, we can find a partition which make U and L really, really close together. And there exists a unique, and remember there's two parts here, right? If you ever see this, exists a unique, you have to prove both that it exists and that it's unique. So then there exists a unique number, the integral of f. Now it turns out that this thing is equal to the infimum of the upper sums over all partitions, which is also equal to the supremum of the lower sums. And that's also something we're going to have to prove. Such that LFP is equal to the integral of f less than equal to UFP for all p. Okay. This is in fact an if and only if. I'm only going to prove one direction for you because in our case, we defined integrability and then say we want to prove that the integral exists. But it turns out the opposite is true. If you can prove that there's a unique number that's all between every lower and upper sum, right? So if you can prove that a number exists which satisfies this, right? So there's one and only one number which is between the lower and upper sum for every partition. That's equivalent to being integrable. So you can try that proof on your own if you want. Again, it's not any more harder than the proof that we're going to do today. And again, hopefully, like intuitively, this is clear. The upper sums are always bigger than the lower sums, right? We know that that has to be true. And I can make them close together. So what must be happening? They must be kind of converging in almost like a squeeze theorem to a single point in between them, right? So that's kind of the intuition. That intuition is going to serve us some, do us some good, but, we still have to prove it. So there's still some work that needs to be done there. Okay, so yeah, there's a lot of things to prove here. In terms of the existence, so basically in terms of existence, I'm going to just prove this. Okay. So this is going to be the existence proof. And if we have the blue thing, the yellow thing follows almost immediately, right? I'll show you. We'll do it in a second. Okay, so what do we want to say? So first thing we need to prove that, or here, maybe let me write this in steps because there's so many things we have to prove. So first, let's show that the inf of UFP over partitions P and the sup of the lower sums exist, right? And to show that, we're just going to show that the set of all upper sums is bounded from below, and the set of all lower sums is bounded from above. That's not too hard, though, because, again, we know that every lower sum is lower than every upper sum, right? And every upper sum is bigger than every lower sum, which means that any fixed partition serves as an upper bound. So what I'm going to say here is, fix, let's just choose the trivial partition. Maybe I'll call that like PT or something for trivial. So that LF of the trivial partition is less than or equal to UFP for all P. Right? i.e. the upper sums are bounded from below, right? I found a lower bound. So that must mean that the inf of the upper sums exists. And by the exact same story, right? That if I take the upper sum on the trivial partition, that's going to be bigger. PT. That's going to be bigger than any of the lower sums. And so the lower sums are bounded from above, therefore their supremum exists. Okay, great. So the inf and the sup both exist, right? And moreover, what do I want to say? The inf the inf of the upper sums also has to be bigger than the sup of the lower sums. So let's do that in a second. First, though, what I want to do is I want to do some notation. I don't want to write inf u f p every single time talking about that number, and I don't want to write sup l f p every time I'm talking about that number. So for notation, what I'm going to do notationally, we're going to write I bar for what I want, the inf of the upper sums, and I lower bar for the sup of the lower sums. Okay, so this is actually fairly standard notation. I with the overline, the bar over top of it, is called the upper integral, and I with the underline is called the lower integral. And some people define a function to be integral when the upper integral and the lower integral both exist, right? It's kind of like one-sided limits, right? And you say that the limit exists if the two one-sided limits exist. This is a similar sort of thing. You've got your upper integral, you've got your lower integral, and your integral exists if those two things exist and are equal, right? So again, this is just a little bit of notation. Try and keep it straight. You can help by remembering that the lower sums are always an under approximation, so the line goes under. The upper sums are always an over approximation, so the line over the I goes above the I. Okay? All right, so 2, let's convince ourselves that the convince ourselves that I bar, the lower integral, is always less than or equal to the upper integral, right? Okay. All right, so what did I want to do for this one again? So I overline is the infimum of the upper sums. Right, okay. So we know that for all P and Q partitions, that we have LFP is less than or equal to UFQ, right? So in particular, if we take the infimum over all possible partitions Q, well, the left-hand side obviously doesn't change, right? Because it doesn't depend on Q. And taking these, infimum on both sides is going to preserve this inequality. and that's equal to I over bar, right? So what we've got is that every lower sum is less than the upper integral, right? No matter what we do, less than or equal to. Q is just a partition. What does the Q under mean? Oh, like that I'm infamizing over all of the partitions Q. So what I could do instead, maybe let me write this on the side. I'm kind of cheating a bit here, but this is a common abusive notation. So when I write inf of UFQ over Q, what I'm saying is take the infimum over the set of UFQ, where Q ranges over all possible partitions. Right, so that is a set of real numbers. So we can take its infimum, and that makes sense. But this is kind of like a standard abusive notation where I'm saying I don't want to write this thing as a big ugly set. So what am I infamizing over? Oh, I'm infamizing over all of the partitions Q, right? And so we might, for example, write this, right? Same sort of thing like we would do when we were doing the infimum of a function, right? On an interval, we'd say, take the infimum of f of x as x, when x is in this interval. And strictly speaking, that's an abusive notation. You have to take an infimum over a set, right? You can't do a function. So same thing over here. This is just an abusive notation, which says, take the collection of all of the upper sums as Q is allowed to vary, and take the infimum of that thing. Okay, does that make sense? Okay, cool. So, okay, if we look at this inequality again, so we have that every lower sum is less than the upper integral. And so in particular, if I now take a supremum over all of the p's, that gives us the result, right? Or in particular, the upper integral is an upper bound for the lower sums. So therefore, the least upper bound is less than it, right? So I over bar is an upper bound. Hence, I lower bar, which is the least upper bound, is less than or equal to the upper integral, right? Is that infimum? Yeah, inf. So T should be an F there. I wrote LFP. Where? So I do want LFP here and here. So I write LFP somewhere else that I don't want? Right, because LFP doesn't depend on Q. So when you infimize it over Q, it doesn't change, right? It's constant in Q. Yeah, so I did mean to take the infimum. It's like if I said, f of x is less than g of y, and now let's take the infimum as y is allowed to vary. And you're like, oh, well, the left-hand side of this equation does not actually vary in that variable. So it's actually just a constant in it, right? So same sort of thing. Okay, so this is good. So this tells us that this is true. And in particular then, what do I want? So what does this say? Thus, LFP is always less than or equal to I lower bar is always less than or equal to I upper bar is always less than or equal to UFP, okay? And this isn't super important for us right now, but where, so LFP is equal to the, look at what I did here. So I took the infimum over Q of LFP, right? And LFP does not depend on Q, right? I'm infimizing over a different partition. So this is constant here, right? Yeah, or if you want, maybe think about it like this. If you look at this equation, this says that LFP, right? If you fix a partition P, that partition, LFP, is a lower bound for every UFQ, right? And therefore, it's going to be less than or equal to the greatest lower bound of the UFQs, right? So that's another way of doing it. if you just want to reason through it like that. But sometimes, like this one actually seems to be giving people a lot of trouble, but I thought it might be a little bit more clear if we tried to do it as kind of like a function thing. Why not less than or equal to? Where? I did write less than or equal to, did I not? Because that's the best you can do. Even if it was a strict inequality. Oh no, because it's the same thing, right? I'm infamizing over the partitions Q. There's no Q's in LFP. It's constant. It's a single set. It's a singleton set. There's only one thing. If I take, right, what I'm saying when I write this is I'm saying take the infimum over LFP when Q is allowed to vary over the partitions. Okay, so there's nothing in the set. There's just a single thing, right? It's just the infimum over LFP, and that is equal to LFP, right? And Mahmoud, exactly, yeah. Okay, is everyone all right with that? So again, maybe if you don't like the kind of calculus of this, where I've taken an infimum over a partition that's not even part of the expression LFP, again, just think about it as saying here, LFP is a lower bound for the set of LF or UFQs. Right? And since it's a lower bound, then the next line, so now it replaced that entire line that have been kind of throwing some people off. If it's a lower bound, it's less than the greatest lower bound, right? And the GLB is I with a bar over top of it. Okay, so which part? Can you be more specific? Like here, let me see if I can give you some intuition too. So, oh, whoa, what just happened? Why did my computer turn off? Okay. Oh, I must have accidentally hit the power bar. So again, I kind of think about it like this. So let's suppose we have the real number line, and I'm going to write it vertically. Okay. So we've got this. So here's the real numbers. Okay. And they're increasing as we go upwards. So there's this special number. We're trying to prove it exists. There's this special number here called the integral of f, right? And the u's, the upper sums all live up here, right? And then the lower sums all live down here. They never pass into each other, right? Exactly, right? The lower sums are always less than or equal to the upper sums. So now what I want you to do is look at this picture and think about if you take the supremum of the lower sums, there's no way it could ever get bigger than the infimum of the upper sums. In fact, even if there's a gap here, and this can happen if your function is not integrable, right? So let's say that the lower sums are down here. Maybe let me use different partitions here just to kind of keep that in mind. Even if there's that gap there and they're not equal, so this is what would happen if a function wasn't integrable, you can probably see from this picture that, yeah, the lower integral, I under bar, is definitely less than or equal to I upper bar. And even in the case where there isn't a gap there, well, okay, those things are going to be equal, but there's no way that under bar could ever be bigger than upper bar, right? Because the lower sums never are allowed to pass into the territory of the upper sums, right? Like they're like hated enemies and they guard their territory. So if the lower sums can never pass into the upper sums, how could the supremum ever get past there either? And that's basically what I'm saying, is I'm saying, look, every single one of these, right, like this lower sum is a lower bound for all the upper sums, right? It's beneath every single upper sum. And so in particular, that tells me that LFP has to be less than or equal to I bar. It has to be less than that thing as well, right? Because that's the least, actually, is that the one I want? Is that oh yeah, that is what I proved, yeah, right? It's lower than everything. So in particular, it has to be at best less than or equal to I bar, right? I over bar. Does that kind of make sense? Does that picture kind of help? Like in some sense, it's like, is there really something we have to prove here? And the answer is yes. Unfortunately, there is. But that's what we're trying to show. Okay, sweet. So I think that picture really helps. And again, this picture right now is of something which is not integrable. But when it's integrable, these two things are actually going to touch, right? That's the idea, is that they get, and you can see that that has to be true. Remember, the definition of integrable is that the upper, you can always make the upper sum and the lower sum arbitrarily close. And you can't do that if there's a gap, right? So basically what we're trying to prove is that there is no gap. And these two things actually have to be equal, that the two I bars have to be the same. No, I mean, in theory, you could choose them such that it's equal. Most functions, these two things won't be equal, right? But you can imagine if the function I gave you was actually a constant function, then LFP and UFQ are always actually just equal, right? They're not actually, one isn't less than the other because the constant function is kind of boring like that. So it is possible that, first of all, the upper and lower sums are just always the exact same thing because they're always just, there's only one of them. And there is no gap. And second of all, here, I'm not trying to guarantee that there's a gap. That's not my goal. I'm just trying to show you the picture of why LFP has to be less than I bar, right? Like there's no way it could possibly be bigger than I bar because the only way that could happen is if LFP ventured into the UFQ territory, and that can't happen. So if you want, actually one thing you could maybe do is try and prove this one by contradiction, right? Suppose that I under bar was bigger than I upper bar. Well, then that must mean that there was an LFP that was bigger than some UFQ, and that's a contradiction, right? So you could do it that way as well. Okay, well, if I took, and not the soup Q LFP, I mean, we could do soup as well, but if whatever I use here, I have to use here as well, right? And I don't want to take the supremum of the u's because the u's might not have an upper bound, right? Like I didn't prove that I can take the supremum of the upper sums because I don't know that they're bounded from above. The only thing I know I can do is take the infimum of the upper sums because I proved that they were bounded from below. So whatever I use there, I have to use on both sides. And I want to take, I want this to show up, I over bar. So that's why I'm using the infimum on both sides. Why do we use the epsilon definition instead of saying there exists a partition I such that I over equals I under? Because you don't know that the supremum is realized, right? Like you don't know if there is, and in generally this will not be true. You don't know that there's a partition such that this is true, right? And this will almost never be true, right? There will not be a partition which actually gives you the lower integral or a partition which gives you the upper integral. The best you can do is, right, just like in a limit, you don't know that the function actually hits your limiting point. You know it just gets arbitrarily close. And it's the same thing here. We don't know that there's a partition that actually achieves the upper or lower integral. We're in some sense limiting. We're getting closer and closer to that value, but we're not necessarily touching it. So this is why we have to use this epsilon delta thing, because the way that we say this mathematically is we don't know that there's a partition which witnesses the supremum, or that we don't know that there's a partition which witnesses the infimum, right? Yeah, exactly. They have to be finite. And if we could totally take like an infinite partition, then maybe we could actually realize the infimum or the supremum, but we can't. So we have to do the epsilon delta stuff. Okay. All right. Maybe I'll leave that picture up because it seemed to be helpful. Okay. So what have I done? All right, let's step back here because what have we managed to achieve? So we've proved that the I bars exist, right? And we proved that the lower integral always has to be less than or equal to the upper integral. That's always true. At no point here have I assumed integrability. Okay, so this result is just universally true. Now what we want to do is basically prove if you're integrable, right? And remember, what does that mean? That means that the difference between the upper and lower sums here, maybe let me put this in red at the top of the screen. If the difference between the upper and lower sums can be made arbitrarily close, then there can't be a gap, in which case the upper and lower integrals have to be equal, right? So again, step 1 and step 2 here didn't actually depend on integrability. So now let's actually prove. So step 3, let's show that they have to be equal. Okay. All right. Now, notationally, this one gets a little bit hairy. So basically what I want to show, so maybe let's say that is, let's show, and I could do the other one. We've got a choice here of what I want to do. I want to show that I bar is equal to the infimum over, let's use just, maybe I'll try and be consistent. I'll use Q, U, F, Q here. Okay. These, and pay attention to notation here. These are not equal, right? I'm not claiming that these are equal. I'm going to prove that these are equal, but this is not the definition of I lower bar, right? The definition of I lower bar is that this is equal to the sup of LFP, right? So I want to show that these two things are equal. So using my notation, I'm going to show that I lower bar is the infimum of the upper subs. Okay, i.e., let's show that for every epsilon, there exists a partition Q such that, okay, so if I'm doing the infimum, what I want is I bar is less than or equal to U, F, Q is less than I bar plus epsilon, right? Yeah, the picture was for non-integrable. If you want to make it integrable, or again, this picture is always true. For integrable, just make the I bars touch, right? Just take the gap away. Yeah. Okay, and then it's integrable. Okay, so let's read this and everyone make sure that you understand what it is I'm trying to do. Remember, I under bar is the lower integral. That number, whatever it is, we proved that it exists, but it is the supremum of the lower sums. And what I want to show is that it satisfies this definition as well, right? And this definition is what it means to be the supremum of the upper sums, or sorry, the infimum of the upper sums, right? So if I can prove this for all epsilon, there exists this partition Q such that this is true, then we're done, because then I've proven that I bar is equal to I under bar is equal to I over bar. Okay. All right. So how are we going to do that? So first one. So in our typical epsilon delta, right? Let epsilon greater than 0 be given. Okay. And let's say, so we know the function is integrable. So pick a partition P, I'm just going to call it P prime, such that U F P prime minus L F P prime is less than epsilon over 2. Okay, we'll see why we're going to use epsilon over 2 in a second. Again, I can do this because I know that the function is integrable, right? I've assumed the function is integrable going into this. So the function is integrable. Okay, and the other thing that I want to do is use the fact that I know what I under bar is, right? I under bar is the supremum of the lower sums. So, so this is since F is integrable. Okay, and let P double prime be such that, okay, so if I'm doing the sup, I want to go down a bit. So I under bar minus epsilon over 2 is less than L F P. It's less than or equal to I bar. And this is since I bar is equal to the supremum of the lower sums. Okay, so the first equation here is the definition of integrability. Maybe let me give it a name. I'm going to call it 1. The second equation here is the definition of the lower integral, right? It is the supremum of the lower sums, which means if you give me an epsilon and I go a little bit to the left, I can find a lower sum which satisfies this identity. Okay. All right. So basically, what I want to do, okay, now what do I want to say? So, okay, let's actually prove the result now. So we know so to prove the result, we already know that I bar is less than or equal to UFQ for all Q, right? This is that picture. Let me, I don't think you drew the, oh yeah, you're right. I didn't draw the double prime. Thank you. Okay. So again, let me remind you of why this is true, why we know that the lower integral is already less than every upper sum. Okay. I'm going to just scroll up to this picture, right? Remember? Okay. So the lower integral, that's that guy right there, is already beneath all of the upper sums, right? That just automatically has to be true. So that part is universally true. It's true for every single partition. So there's nothing to prove there. Okay. So we already know that the lower integral is always less than or equal to UFQ for all Q. We just need to show the other part. We just need to find a partition P such that, or again, maybe let me call it Q. Q such that UFQ is less than the upper bar plus epsilon, or under bar plus epsilon, right? That's this part. So we're saying this part, always true. So let's prove this part. Okay. And the way that I am going to do that is basically just to combine 1 and 2. All right. Okay, so how am I going to do that? Let's take a look here. It's pretty much already done for us. So what I'm going to do is the following. So from equation 2, we're going to get that negative I bar. I like to just write this out just because if I didn't write it out, I would script the signs. Actually, here, let me say this. So set Q. Let me just double check because it sounds like my computer's dying and it shouldn't be. Oh, no, that's something else. Who cares? Okay. So let's let Q be P union P double prime. Now, because I've refined the partition, that guarantees to me that both equation 1 and equation 2 are still true with Q. So that 1 and 2 both hold. Okay, and again, you're gonna have to convince yourself that that's true, but it's not hard because by what we did on Tuesday, again, we know that when we refine partitions, the upper sums get lower and the lower sums get taller. So what that means is that equation 1 is still true because the gap between U and L is actually gonna get smaller, right? So if the gap was already less than epsilon over 2, when I refine it, the gap gets even better. And with equation 2 here, again, the refinement is actually gonna get bigger. So I'm gonna get that I minus epsilon over 2 is less than LFP double prime. That is also going to be less than or equal to LFQ because refinements get bigger. That still has to be less than or equal to I bar. Okay. So convince yourself that both 1 and 2 still hold, right? Moreover, like I said, now I'm going to write this out because I will definitely screw up the signs if I don't. Like so. Okay. And now I'm going to add, what do I want to do here? Right. Yeah, so I'm going to now take this and I'm going to shove it into equation 1. Right? Okay, so I'm going to get UFP then. So into equation 1, we're going to get UFQ minus LFQ. So this is already less than epsilon over 2. We know that. And I'm also going to get, if I use, damn it, which side am I doing here? Plus I bar, which side am I doing? P minus I bar, right. Right. Yeah, okay, here, let me maybe state this a different way. Let's add UFQ to this. So we're going to get UFQ minus I lower bar is less than or equal to UFQ minus LFQ, right? Now this is less than, what do I want here? It's less than epsilon over 2. Maybe I didn't need the epsilon over 2 because I'm done, right? Right, like I'm not even using this side. Because now I've gotten that UFQ is less than, so let's ignore now this middle part. So if we ignore this, we get this is less than I bar plus epsilon over 2, and that's less than I bar plus epsilon, right? And that's what we wanted to prove. So yeah, I guess I didn't even need the epsilon over 2. I could have just done epsilon. Oh, well, yeah. Hey, listen, if it works, right? Okay, great. So thus, I lower bar is equal to I upper bar, right? Is 2 supposed to be less than or equal to? What, right here? That one should be a strict less than. Right? When you add UFQ to 2, wouldn't the right-hand side make a difference? Yes, but I'm basically ignoring the right-hand side. Right? So I'm actually not using this. All right? So ignore that. Now add UFQ to both sides. Right? So I get this equation here from this equation here, just by adding UFQ to both sides, right? Because you're allowed to do that. That's okay. And then here I use equation 1 in order to conclude that that's less than epsilon over 2. Yeah. And then this is where I'm saying I didn't actually need epsilon over 2 here. I thought I was going to add these, but I didn't. All right, so I actually just needed that it was less than epsilon. Then I can move the lower integral to the right-hand side, and that gives me the result that I wanted. Okay, so yeah, it's equal. So this is equal. Now, by definition, this is going to be, so if now the integral of f is equal to I lower bar is equal to I upper bar, then we said before, right? So where did I write that? Right here, right? So now if I take this equation, that means that LFP is less than or equal to the integral of f is less than or equal to UFP for all partitions P, right? So it exists. That's what we've proven. You have to confirm it's unique, but pretty much that's a very quick proof. So I'm going to leave that too because we are running out of time. Okay, so check it's unique. But again, hopefully, and I say hopefully because it kind of assumes that you've been following, and I suspect that I've lost a lot of the class at this point. But hopefully you can see that it has to be unique. Because again, by this picture here, so if we let me now draw the picture for integrable. Okay, so this is going to be integrable here. So if I draw the picture, here's the integral of f, right? Here are the upper sums. and here are the lower sums, right? And again, they kind of smush together in the middle there. Could there be another number there? And the answer is obviously not, right? Like they're already in the integrable case, these two things come together and they smush together. There can't possibly be another number between them, right? There's only one number. When there's a gap, when the function is not integrable, look, there's lots of functions in here, or lots of numbers in here between the upper and lower integrals. But when the upper and lower integrals are equal, there can't possibly be a number in there, right? So I would say, actually, we could just maybe argue that. Right, clearly, since the upper and lower integrals are equal, there can't be another number in here, right? So since, LFP is less than or equal to I bar is equal to I upper bar is less than or equal to UFP, there cannot be any other number which is always between the upper and lower sums. And UFP for all P, right? Because any such number must be between the lower integral and the upper integral. But if the lower integral and the upper integral are equal, that's the only number it could be, right? So hopefully that makes sense. Was there anything else I needed to prove? So I proved they existed. I proved it was unique. I've proven that they're equal to the upper and lower integrals. No, I think that's it. Right? Cool. All right. Now, on the basis of this, who's freaked out by integration? Is anyone just like, oh no? Yeah. This is one of the hairier proofs. I think that this is there's definitely some stuff to do here. I also think that, like, again, this proof is not, it's one thing to watch someone try and prove things, right? It's a different thing to try and do them yourself. I think just on the basis, like this proof took us an hour, right? And I think just on the basis of how long this proof is, there's almost too much there for you to try and internalize all at once. Yeah. Pictures are great for intuition, right? But at the end of the day, you got to prove it. Yeah, exactly. Maybe that's a better question, is who isn't scared? But what I really recommend you doing is going through and trying to replicate this proof on your own at some point and just get as far as you can, right? Like if you can't go start to finish all at once, it's totally okay. This is probably, like I said, it's one of the nastier proofs that we're going to see, I think, period. So it's a nastier proof that we're going to see, and it's right at the beginning, right? So as you start to get a little bit more comfortable with doing integrals, I think this won't be as scary anymore, but this is day 2 of integrals, and you already get hit with one of the worst sort of results that you have to see. So, I mean, it's probably just too much too quickly, right? Unfortunately, we can't really avoid it. We've got to do it because we needed these results. But I'm willing to bet if you go back, 3 or 4 weeks from now, when you're much more comfortable with doing these sorts of proofs and you look at this proof, you'll be like, oh yeah, that wasn't that bad. Okay. So maybe just put a little star beside this one and be like, write yourself a note. This is total nonsense now. Maybe like go back and look again in 3 weeks or something and see if it makes sense then. And that would probably be a good exercise. And the sort of thing too, that would be really good when it comes time to study for your next term test, is to go back and see if you can do this proof, right? Maybe without even looking at my solution. And again, my proof here isn't the only way you can do this. There are a couple of places where you could have done it by contradiction if you wanted to, and you could have gotten a perfectly reasonable and valid proof that way, right? From the inequality, sure. Yeah, okay, so basically what I'm doing, so this right here, maybe let me kind of change this and then I'll change it back. So let me write little m here. This is the definition of what it means for m to be the infimum of the upper sums. Right? This is the epsilon definition of the infimum, right? And what I'm trying to show is that the infimum of the upper sums is equal to the supremum of the lower sum. So what I'm going to do is put sup LFP in here. I don't really have a lot of space. Right? So I'm trying to show that the supremum of the lower sums is the infimum of the upper sums. So what I'm doing is taking the supremum of the lower sums and shoving it into the definition for the infimum of the upper sums, right? And then, I didn't want to write sup LFP everywhere. So I replaced that with I lower bar, but that's what we're trying to do. So if we can show that this, blue box is satisfied, then that would show that sup of the LFPs is equal to inf of the UFPs. And that is precisely the statement that I upper bar is equal to I lower bar, right? So I took this and shoved it into the definition of this in order to prove it. So does that make sense? And so that's why, yeah, exactly. So we were proving the second half of this inequality. That's kind of what the long proof is. So we were proving that gave us that the lower integral satisfied the definition of the upper integral, and so they had to be equal. Yeah. Okay, everyone? So yeah, we're not going to get to actually doing an example of an integral today, which is going to be fun because your next assignment has such an example, but I'll do it first thing on Tuesday. So hopefully it shouldn't, throw you off too much. Okay. All right, any questions, anyone? Yeah, no problem. I guess I put a little star here, everyone, and just remind yourself to come back and look at this in a couple of weeks when you're a little bit more comfortable with this material, and hopefully it'll make more sense. Okay, awesome. Thanks, everyone. Have a good weekend, and I will see you next week. And by the way, yeah, in case you didn't notice, and I'm sure you did, the assignment is up, so take a look at it. And then otherwise, like I said, have a good weekend, and I'll see you on Tuesday.